Cool runnings, the world of marine refrigeration. In the marine world, refrigeration plays a vital role for the ship's cargo and crew. This video will explore how the refrigeration cycle works and describe the vital equipment and processes in the vapor compression cycle. Finally, we'll look at a few systems and applications of refrigeration. But first, we need to take a closer look at how refrigeration systems work. Modern cycle refrigeration works by moving heat from a cold place to a warm place. Although this seems to violate the laws of thermodynamics, refrigeration systems use thermodynamic trickery to remove heat from the space by performing work on a refrigerant, the working fluid in refrigeration cycles. Areas where refrigeration is maintained are known as zones. These zones can consist of food storage containers that must be chilled or most commonly found on domestic refrigerators and simple air conditioners. The vapor compression cycle performs the fundamental processes of the refrigeration cycle. It shares many similarities to more complicated systems. First, we'll take a look at refrigerants. Refrigerants are the working fluids in the refrigeration cycle. The refrigerant picks up heat and transfers it to the space outside of the zone. Refrigerants vary and depend upon their application. The specific refrigerant should evaporate at the desired cooling temperature and recondense at the sink. Additionally, the refrigerants should be low cost, preferably non-toxic, chemically inert, environmentally friendly, and non-flammable. For the chemistry of refrigerants, we'll turn to our local expert, Spencer Dugan.
Sorry, didn't see you there. Fluorocarbons are the most popular refrigerants today. These consist of either hydrofluorocarbons, chlorofluorocarbons, or hydrochlorofluorocarbons. However, only hydrofluorocarbons are allowed on new systems today. A common new refrigerant is R134A with a boiling point or vaporization temperature of negative 15.7 degrees Fahrenheit.
The compressor. The refrigerant has its pressure and temperature increased by a compressor. These compressors are usually positive displacement and require power in order to be driven. The condenser. After flowing through the compressor, the refrigerant is delivered to the condenser. The condenser acts similarly to a heat exchanger. This is where the superheated vapor releases its heat into the surroundings. The pressure of the refrigerant is kept constant while the gas changes phase into a liquid. The temperature is also lowered, leading to a subcooled liquid at the exit. The expansion valve. The expansion valve is the most magical part of the refrigeration cycle. For a better explanation of expansion valves, we'll take it to our refrigeration expert, Spencer Dugan.
While most systems use a thermostatic expansion valve, this valve is designed to ensure that a minimal amount of liquid enters into the compressor. So what this valve does is it functions similar to a balloon, and the temperature at the evaporator controls the temperature of a volatile liquid placed inside the valve. When a high temperature is sensed at the evaporator, the volatile liquid expands, causing the balloon to expand and exert a higher force upon the valve. This limits the gas produced by the valve, meaning that more liquid will come from the thermostatic expansion valve.
The evaporator. The mixture produced by the expansion valve then passes through the evaporator. This cold mixture absorbs heat from the space, causing the remaining liquid to vaporize. The gaseous refrigerant is pulled through the evaporator back into the condenser, completing the thermodynamic cycle. Insulation. In addition to the thermodynamic cycle is insulation. Insulation reduces the ability of thermal energy to permeate enclosed spaces. Insulation is vital in carrying products such as LNG. It also lessens the loads placed upon the refrigeration cycle.